examples of exponential functions. We're going to start with our first one here, and we're graphing the parent function as well as how the graph has been shifted. So, first one here, we have this function 3x, or 3 to the power of x. And then we're also going to graph how it's been shifted. So plugging in values here, we have -1, 0, and 1. And we'll learn really quickly that we don't need nearly as many points as we did in the examples in the beginning of this section. Pretty soon we'll be comfortable enough with just plotting maybe 3 to 5 points. Now if I plug in -1 here, I'm going to have 1/3. If I plug in 0, I'm going to have 1. If I plug in 1, I'm going to have 3. And that's enough for me to figure out what basically this graph looks like. Knowing that this is an exponential function, knowing the shape of graph that I'm graphing, this is enough for me to know what this looks like. So I'm going to go ahead and graph that. And I know that I have an asymptote at the x-axis here, so I want to make sure I include that. And now let's go ahead and graph g of x. Now, g of x is the function f of x, but it has shifted to the left 1. So all of these points are just going to move to the left 1. Okay. So it's like all I did was move these a little bit. So now when x equals -1, our function equals 1. When it equals 0, it actually equals now 3. And I'm going to add the point -2 here. And when x equals -2, it equals 1/3. So those are my new points. And I can draw that graph, and it actually does not change my horizontal asymptote at all, because shifting over this asymptote, it's still in the same spot really. Now, here in this next example, we have the natural exponential function. We have base e. So we're going to start off graphing with x and then f of x. And I'm going to choose the same values, -1, 0, and 1. And when I plug in -1, I have 1/e. Okay. And that's like 1/2.7, so it's a little bit less than 1/2. Okay. Now when I have 0, well, anything to the 0 power is just 1, and then plugging in 1, I have e, which is 2.718. Okay. So let's go ahead and graph this example here. And I have my graph here. And at -1, it was 1/2.7, a little less than 1/2. At 0, it was 1, and then 2.7. So just like many of the other exponential functions we've drawn, this is what it looks like. And then I've got my horizontal asymptote. And now I want to graph this function here, which has been shifted. So I have g of x, and this has been shifted down 3. Okay. So down 3. So each one of these points is just going to move down 1, 2, 3, down 1, 2, 3, down 1, 2, 3. Now that also changes my horizontal asymptote. My horizontal asymptote is going to move down 3 as well. And that's because it's a vertical shift as opposed to here where it was a horizontal shift. So my new function looks like this, and it's approaching that line now. And these points right here, if we move this down, that would be like 1/2.718 minus 3. And you can calculate that decimal. I'm not too worried about that. 1 minus 3 would be -2. And then same thing here, minus 3 would be -0.3, actually 282, I believe. Okay, so you can calculate those decimals with your calculator. But really what I'm concerned about is seeing them graphed correctly here. I'm less concerned about this table as long as I can see this one correctly. Now we've got one more example here. And this one I'm not asking you to graph two different functions. However, if it's helpful for you to graph the parent function first, you're more than welcome to graph the extra function there. Okay, so let's go ahead and set up our graph here. And setting up my table. And I'm actually going to not call this h of x since that's h of x. We'll call it f of x. And I'll let f of x be 1/3 e to the x. Alright, so f of x is going to be 1/3 e to the x. Now plugging in -1, well, I have e to the x here that's going to be moved into the denominator, and I have 1/3e, okay, which is a little bit more than 1.9, or 1/9. Okay. If I have 0 there, then that's 1, and that'll just be 1/3. And then if I have a 1 there, well, that's going to be e divided by 3, and that's a little bit more than 1. We're just rounding decimals. If you want to plug these in your calculator, if you don't like using fractions like that, that's okay. You can figure out what the decimals are. That's fine with me. So plotting these points here, 0 was 1/3, and then we had e divided by 3, which is a little bit more than 1, and then -1, we had 1/9, really low decimal. So this function is not growing quite as fast. It's still a growth, but it's a flatter growth function. Now let's look at shifting that graph for those values. So this shift right here is going to move me to the left 2. So each one of these points is moving to the left 2. And I'm actually not going to fill out the table. That's fine as long as we can tell which one these is. And notice I've color-coded everything, so you know that this is h of x. But if you're doing all of your homework in one color, you need to label them like this so that I know which graph is which. And then the only thing I have missing is my horizontal asymptote. So those are some examples of graphs that we can look at. And I'm going to go ahead and flip the page now, and we're going to talk about how we really apply exponential functions to being useful in real life. And this is probably one of the most useful lessons in the whole year. We're looking at compounding interest, and we can look at a P, your principal amount of money that you put into, let's say, a bank account. So we put in a certain amount of money, and then we have a percentage rate that we're earning money on that money that we put in the account. A is what we've accumulated plus what we initially put in over the course of a certain amount of years. Well, if we just figure this out 1 year, then this is what we put in at 0 years. No time has passed at all. We just have our principal, the amount we initially put in. After 1 year, this is what we'd have left. And this is part in the parentheses here is what we're going to earn every single year. So then after 2 years, that would be squared, and so on. And after t years, that would be to the t power. Now that would be calculating our interest only once a year, but it can be compounded more than once a year. We can compound it n periods per year. So if I compounded it quarterly, that would be 4 times a year. Semi-annually, another way you could see that is biannually, it's 2 times a year. Monthly would be 12 times a year. Annually is just once a year. Weekly, I could say 52 times a year, but these are the ones that we see the most. So that's how many times a year we would be compounding our interest. Now this is a formula you're going to need to know, so make sure that you know this formula right here. And R is our percentage rate, N is how many times a year we're compounding our interest, T is how many years the money is in the account, and P is our principal, the amount we initially put in. A is what we've earned over a certain amount of time. Now, we can compound our interest faster and faster. So like I said, it could be semi-annually, twice a year, or 4 times a year, or monthly, do it 12 times a year, or I could say I wanted to do it weekly, 52 times a year, or let's say I wanted to do it daily, 365 times a year. I'm compounding my interest. I'm calculating how much interest I've earned on my money. But what if I said I wanted to calculate my interest every second? Well, every second then I'd be calculating interest and earning money faster and faster and faster. The more times that we calculate our interest, the faster our money is growing and we're getting more and more money. But we can compound our interest, what we say, continuously, or continuous compounding. That means faster than every trillionth of a second. So almost instantaneously we're calculating our interest. And that's the best option that we can find. So we're going to look at an example here. And it says, find the accumulated value of an investment of $5,000 for 10 years at an interest rate of 6.5% if the money is compounded semi-annually, quarterly, monthly, and continuously. So I'm going to go through these, the first three pretty quickly because they are all similar. So A, compounded semi-annually. I'm using this formula that we see right here. We put in $5,000 for 10 years, and my interest rate is 6.5%. So A is equal to 5,000 times 1 plus N is semi-annually, so that would be 2. And my rate is 6.5%, so 0.065. I'll go ahead and zoom in a little bit here. And then my exponent here, N, is 2. And then my rate, or my time, is for 10 years. Now, all you're going to be doing is plugging these in your calculator. So I'm going to go ahead and set up all of them at once, and then I'll pull out my calculator and show you how to calculate them. Now, quarterly, we said was 4 times a year, so 4.065. A lot of this stuff doesn't change. 4 and 10. We can plug that in our calculator. And C, A equals 5,000, 1 plus 0.065 over monthly would be 12 times a year. You can plug that in our calculator. And I'm going to do this last one in a different color because we're using a different formula. We're using this formula right here. So A equals 5,000 e to the 0.065 times 10. And then we can plug that in our calculator. So, pulling out my calculator, I'm going to go ahead and try and get all of this in the screen at the same time. So, let's see if I can fit everything. Okay. So, this first formula right here, okay, I'm plugging all of this in. So 0.065 divided by 2 plus 1 to the 20th power times 5,000. And that's how much I'll have after 10 years. Now, we're talking about money here, so we want to make sure that's the way we write our answers. So 9479.19 is what I'll have after that amount of time. Now I'm going to calculate the rest of these really quickly. Okay, so we have, let's see. Actually, I'm going to skip because my video is about to run out. I'm just going to skip to this last one. Plugging these two in is very similar, and you can go ahead and do that on your own calculator. For this last one, we want to plug in 0.65 or 0.065 times 10 and e to that power times 5,000. And that's our answer.